Hello and welcome to this chemistry lecture series. In this video, we're going to cover chapter 15, section 4, which is going to look at another type of reactions of alkenes. In this reaction series, we're going to look at the oxidation reactions of alkenes. Just to remember, early on in the last section, we went over the addition reactions of alkenes. Now we're going to look at oxidations. Now, to debrief a little again, or recover again a little bit what oxidation is in organic chemistry. In organic chemistry, the term oxidation is used for when the organic compound is oxidized. Oops. So we're going to look at how when the organic compound is oxidized, meaning that the organic compound is either going to gain oxygen or lose hydrogen, or both. So this is the way in which we view oxidation in organic chemistry. It makes it easier than counting electrons and oxidation numbers, especially when we have a lot of different atoms involved, different carbons, hydrogens, oxygens, etc. So this is going to be the oxidation of alkenes. And now oxidation in organic chemistry, as it did in inorganic, usually involves one of two oxidizing agents. The most common oxidizing agents we see in chemistry, especially in the AICE curriculum, are potassium permanganate, KMnO4, potassium dichromate, K2Cr2O7, and sometimes, rarely, there are reactions where sulfuric acid, H2SO4, acts as an oxidizing agent. So this is more rare. So we'll put here more rare. But if you see potassium permanganate or potassium dichromate in a reaction, automatically you know that reaction is an oxidation reaction. So do keep that in mind. It does make it a little easier to deal with trying to predict the types of reactions that are going to happen when you see one of these two compounds in there, because you know that there's going to be an oxidation reaction. So let's get started with how these oxidation reactions happen in alkenes. Oxidation of alkenes can happen actually in two different ways, and they involve the same reactant. So an alkene can react with acidified potassium permanganate at room temperature to undergo an oxidation reaction. But in this case, we have the conditions that are going to affect our outcome. If we react the alkene with dilute acidified potassium permanganate at room temperature, what we are going to get out of this reaction is a diol. Remember, di means two, ol means alcohol. So a diol, being our product, is a 2-hydroxyl group alcohol, meaning that it has two OHs on it. This is going to happen when we react the alkene with cold dilute potassium permanganate, or cold meaning room temperature, not heated. The other thing that you might notice is that the potassium permanganate here has to be acidified. Acidified meaning that we have added either hydrochloric acid or sulfuric acid or some kind of acid that provides hydrogen ions to the potassium permanganate. This is because those hydrogen ions are necessary for the mechanism of this reaction, which we're not going to look into. But all of these different parts are important here. The alkene has to react with acidified potassium permanganate, meaning that it has to have an acid in it. It needs to be dilute and at room temperature to get the diol, or we're going to get a different product that we'll see in the next slide. So we have here some conditions with some reactants and some products. So this reaction, what it's going to do is that we call this a mild oxidation reaction. The reason we call it a mild reaction is because we're not fully breaking the double bond. Because the conditions are mild, because it's cold and it's dilute, when the oxidation happens, it doesn't break the whole double bond. It only breaks the pi bond in the double bond. It only breaks one of the two bonds. And that reaction makes the alkene react with water because it's dilute and the oxygens from the oxidizing agent, the potassium permanganate. Remember that we're not going to draw potassium permanganate as KMnO4 in this reaction. Whenever we have an oxidation reaction in organic chemistry, that KMnO4, the oxidizing agent, simply gets put in as O in brackets, showing the oxygens that reaction is providing. Now, when this happens, the double bond, the pi bond in the double bond breaks, and hydroxyl groups, OHs, are added through the double bond. So we're exchanging the double bond for two OHs, one in each carbon that had the double bond before. So in this reaction, we're going from an alkene, let me write that here, we're going from an alkene, to a diol. And again, diol meaning a double alcohol. There is an observation that goes along with this reaction as well. Because potassium permanganate is purple when it's just the potassium permanganate, once the potassium permanganate reacts with the ethene, it actually loses its color, turning into the colorless manganese 2+ ion. Meaning that this reaction is going from purple to colorless when it happens, or we can say that the solution decolorizes. So let me write that on here, decolorizes. So the solution decolorizes from purple to clear. This makes potassium permanganate another good test for a double bond. So we already saw how we can use aqueous bromine or bromine water in section 3 to test for a double bond, the carbon-carbon double bond. We can also use cold acidified potassium permanganate. If we add cold acidified potassium permanganate to an unknown that we suspect has a double bond, if the solution turns colorless or from purple to clear, then it's a good indication that that compound has a double bond. Now, since we only care about what happens to the organic compound in the reaction, again, we can usually replace the KMnO4 with that O in brackets. We will be able to do the same thing if this reaction was carried out with potassium dichromate. We will see that O in brackets as the oxygens from the oxidizing agent, because that's what the potassium permanganate is contributing here. So the reaction, again, of alkenes with cold dilute acidified potassium permanganate is going to give us a diol. We're going to break the pi bond and the double bond, put two hydroxyls, one on each carbon, and that creates a diol. So for example, ethene would create ethane 1,2 diol. Now this is one of the two oxidation reactions. The other oxidation reaction happens when we change the conditions. So if we use the exact same reactants, so if we used an alkene, and again underline here because it's a reactant, so if we used an alkene with potassium permanganate, and again this will be acidified potassium permanganate, we don't have it here, but this will be acidified potassium permanganate. If we reacted an alkene with potassium permanganate, but we now change the conditions. If we change, instead of cold dilute permanganate, we used hot concentrated permanganate. So we do not change the reactants, but we do change the conditions. Then we get a different product. What happens is that when we use hot concentrated potassium permanganate, we have a more extreme reaction or a more drastic reaction. So because the conditions are more extreme, we have a more extreme oxidation reaction when we use hot concentrated potassium permanganate. And the reaction, what's going to happen is that it's going to, instead of only breaking the pi bond, it's going to completely break the double bond on the alkene. The products of this reaction, because we're completely breaking the double bond and we're essentially attaching an oxygen to it, are going to vary depending on the type of carbons in the double bond. So what happens? If we have a carbon with two hydrogens, or essentially what we call a terminal carbon on the double bond. So if that carbon, if one of these carbons has just two hydrogens on it, it's a terminal carbon, then the product we're going to get out of the reaction is carbon dioxide. Terminal carbons, carbons with just two hydrogens on them, are going to get converted to carbon dioxide as a product. If we have that reaction happening on a carbon that has one hydrogen and another carbon chain, remember R just means a carbon chain, what's going to happen is that that carbon will get turned into an aldehyde. So the carbon with the one hydrogen on it and the one carbon chain will get converted to an aldehyde because the carbon-carbon double bond breaks and creates a carbon-oxygen double bond. So notice how the R group and the H stay the same, but the double bond gets turned from a carbon-carbon double bond to a carbon-oxygen double bond, creating our aldehyde. And if that aldehyde is left to stay in this reaction, if we do not remove the aldehyde from the reaction, it gets further oxidized into a carboxylic acid. And we're actually going to learn about this reaction in chapter 18, where an aldehyde can also be oxidized by the exact same conditions into a carboxylic acid. So if there's a carbon on the double bond that has a carbon chain and a hydrogen on it, that carbon's going to get oxidized into an aldehyde, which then, because it's sitting in the reactants, in the potassium permanganate, is going to be further oxidized into a carboxylic acid. So this happens a bit like a two-step reaction because we're not separating that aldehyde from the reactants that it also reacts with. And then if we have a, let me change the color here. If we have, let's use blue. So if we have a carbon on the double bond that has two carbon chains on it, so essentially that double bond stuck in the middle of a lot of different carbon chains. So that carbon with two carbon chains on it will get oxidized into a ketone. So that carbon, again, we're going to break the double bond, and instead of carbon-carbon double bond, we're going to have a carbon-oxygen double bond, creating a ketone since that carbon is bonded to two other carbon chains. So what we get out of the reaction with a concentrated potassium permanganate will vary depending on the structure of the alkene. The carbons on the double bond that have two hydrogens will get turned to carbon dioxide. The carbons on the double bond that have a carbon chain and a hydrogen will turn to an aldehyde, which will then further oxidize into carboxylic acid. And then the carbons in the double bond, if there are any that have two carbon chains attached to them, will get turned into ketones. So again, this is because the reaction is much more extreme since it involves hot concentrated potassium permanganate, more extreme conditions for the reaction. So how do we predict products, right? So imagine you have a reaction. You're talking about a reaction here, and you're asked, what is the products of this reaction? How do we predict the products of an oxidation reaction where we have hot concentrated potassium permanganate being used? Well, what you will use in this situation, if we need to identify the carbons on the double bond. So we're going to find the double bond on our alkene that's reacting with the concentrated hot potassium permanganate that's acidified, and we're going to put a line through it. Oops, let me use a smaller line. We're going to put a line through it. That's going to be the double bond that we are breaking. And then once we put a line through it, we are going to identify what type of carbons are on this double bond. So we're going to identify, once we put a line here, what type of carbons we have. The two carbons here and here are going to be this one, which has an R group, a carbon chain on it, and a hydrogen, because remember, there's a bond here missing, 1, 2, 3 bonds, which means that there is here a hydrogen that we're not seeing on this bond, meaning that this carbon has a hydrogen and an R group on it. As we saw earlier, carbons that have a hydrogen and an R group are going to be turned into aldehydes, that then get further oxidized into a carboxylic acid. The other carbon that we have here is a carbon with two R groups. We have a carbon chain here. There's a CH3 up here. That, again, it's just that terminal carbon right here. And then we have a 2 carbon chain here. Remember that carbons that have 2 R groups on them are going to be turned into ketones. So what are we going to do here? We are going to cut this double bond so that we separate our 2 carbons. So we are very literally going to cut the double bond, which gives us this on one side. So let me highlight what we're looking at here. So this cut, we're going to get this double bond with the 1 carbon here, which is what we're looking at here. And then on the other side, we're going to get the double bond with a CH3 on one side and a CH2CH3 on the other, which is what we're looking at here. Once we do that, once we have separated our double bond into the CHR1 and the CR2 we know this is going to be oxidized into an aldehyde, and this is going to be oxidized into a ketone. How do we do that? We're simply going to add an oxygen to this double bond. Because that's what happens here. Whenever we cut the double bond, we oxidize. Remember, oxidation is the addition of oxygen. So once we separate the double bond, we're just going to add an oxygen to it. So we have now our oxygen, our aldehyde here. Because remember, there is still that hydrogen hanging out here that we're not seeing. So there's a hydrogen here. So we have our aldehyde, COH, and then our ketone here, CO, and then R group. But remember that that aldehyde is going to be further oxidized into a carboxylic acid. So once we have our aldehyde and our ketone, we do need to further oxidize this aldehyde into a carboxylic acid by adding an OH there to the bottom. And these are our actual products, our carboxylic acid and our ketones that get created from this reaction of an alkene with hot concentrated potassium permanganate. And it's acidified with H+. So that's how we predict the products, right? We cut the double bond, separate the 2 molecules we're going to get, because this is a case where we go from 1 molecule to 2. We're going to cut the double bond, put oxygens at the end of those double bonds, and if it's an aldehyde, we need to then further oxidize it into a carboxylic acid by adding the OH. If one of these was a terminal one, where we have a CH2, then we would just make carbon dioxide, CO2 out of it. How do we go backwards? Well, we go backwards the same way, but, backwards. So to predict the alkene that gives us 2 products, so imagine we are told we get an alkene reacting with hot concentrated potassium permanganate, and we are going to make carbon dioxide and this carboxylic acid out of it. Then we just think backwards, right? We work from the products backwards. Based on the products, we know that the carbon on either side of the double bond is the one where the double bond was originally made. carbon dioxide, anytime you see carbon dioxide, you know it's a result of a CH2, where a carbon had a double bond with the two hydrogens on it. And if we see a carboxylic acid, then we know the original carbon was a CHR, where we have a carbon chain of some kind bonded to the double bond and a hydrogen on the other side. So the double bond here comes from, because we have CO2, it comes from a CH2, where we have carbon with two hydrogens on the double bond. And then the other side of the double bond in the carboxylic acid comes from a double bond with a carbon hydrogen and an R group. What is our R group is one of the things that we're going to have to figure out. Well, we'll talk about that in a second. But first, let's turn this into what they come from. So essentially, these now get turned into this and this, where our R group here, so let me highlight the R group. Our R group that we have here, because we use the R group to make it more generic, is this carbon chain right here. This 3-carbon chain attached to the double bond carbon. Once we have our two pieces, once we know the carbon dioxide came from the CH2 with a double bond, and the carboxylic acid came from the carbon double bond with a hydrogen on one side and the R group on the other, what we need to do is we need to connect the double bonds. We need to grab this part of the double bond and connect it to this carbon right here. And so what we get once we do that is this. We get our carbon that's double bonded with that blue section, right? So this blue section right here is this. The hydrogen is not shown because it will be right here. But again, we don't show that hydrogen because it's a skeletal structure. So it'll be right here, even though we're not showing it. And then we have our carbon with two hydrogens. That carbon is right here. Remember, we don't show hydrogen, so this is a carbon, this is a CH2 right here, which is this CH2. So we're just joining the double bond. This is going to become one double bond together. Because what we're seeing here is essentially two halves of the same double bond that's connected. All right? So that's going to be our product here. That is going to be the whole reaction. We're have carbon 1. And that's going to connect then over to carbon 2 here, and 3, 4, 5. So this is the alkene that originally created those products that were given, which were CO2 and the carboxylic acid, C double bond O, OH, 1, 2, 3, like that. So these were the original products we were given at the beginning. This is an alkene that when reacted with hot concentrated potassium permanganate creates those two products. And again, that product was the result of this part of the alkene being broken and turned and oxidized. And the carboxylic acid was a result of this part of the alkene being turned into an aldehyde and then into a carboxylic acid. So that's how we figure out the reactant, the alkene that is the cause of the products here. Whereas earlier we saw how we will figure out the product from the alkene. Well, that's it. That's it for the oxidation reactions. Remember, there are two different types of oxidation reactions of alkenes, depending on whether we are using hot concentrated potassium permanganate, which is going to break the double bond completely and give us a plethora of different types of products, or if we use cold dilute potassium permanganate, which gives us the diol because it only breaks the pi bond on the double bond. Well, that's it for section 15.4. I will see you in the next video to start talking about polymerization reactions in alkenes.